So here's a thought to kick things off. What if AI could learn, like really learn, become super intelligent without needing tons and tons of data labeled by us humans?
Mm.
Imagine an AI that just trains itself, pushes its own
That's
limits.
exactly the territory we're exploring today.
Yeah.
It's pretty fascinating stuff.
Yeah, today we're diving into this really groundbreaking new framework. It's called R0.
Right.
And it proposes exactly that, a fully autonomous, self-evolving large language model, an LLM that basically generates its own homework, its own training data completely from scratch.
So a radical idea, really.
Mm.
For this deep dive, we've got this technical report, R0, Self-Evolving Reasoning LLM from Zero Data.
Okay.
And our mission for you listening is to sort of unpack how this R0 thing works, this ingenious mechanism behind it,
Uh-huh.
look at the results they got, which are pretty impressive, and then think about what it all means for, the future of AI.
Right, like a shortcut through the jargon to get to the core idea.
Exactly. We want you to understand how some of this cutting-edge AI is actually learning right now.
Okay, so let's start with the problem. Why is something like R0 even needed? What's the big challenge in AI training it's tackling?
Well, the current way we train most of these big, powerful LLMs heavily relies on just massive amounts of human effort.
Human-curated tasks and labels, the report calls it, for fine-tuning and all that.
Precisely. And this isn't just a small inconvenience. The report calls it a fundamental bottleneck
A bottleneck, okay. Why fundamental?
because it's incredibly costly, labor-intensive, and difficult to scale. Think about it. If every improvement needs humans to meticulously create and label data, there's a limit, right?
Mhm.
It really slows down how fast AI can potentially surpass, human capabilities.
Yeah, that makes sense. You can't scale human labelers infinitely. So before R0, people were already trying to fix this, weren't they?
Oh, definitely. There were attempts.
Like label-free reinforcement learning. I remember hearing about that. What was the deal there?
Yeah, label-free RL. It was a step. It could get reward signals from the model's own outputs, so you didn't need explicit human labels for every single thing.
Okay,
But
there's always a but.
the but was it still needed a pre-existing corpus of tasks. You still had to give it the problems, even if you didn't give it the answers. So not quite starting from zero.
Right, not truly autonomous learning then. What about those self-challenging approaches, where the AI tries to make up its own
That was
problems?
another interesting direction. Models generating their own tasks.
Yeah,
Sounds great on paper.
another but.
Uh-huh. The problem often came down to verification. How do you know if the answer to the self-generated task is actually correct?
Ah.
They often leaned on external code executors. Fine for math problems or coding where a program can check the answer.
Yeah, like 2 plus 2 equals 4, easy check.
Exactly. But what about, say, evaluating a poem the AI wrote itself? Or answering a complex philosophical question it posed? There's no simple external checker for that kind of open-ended reasoning.
Right, that's much harder. So these previous methods had limitations, which brings us back to R0.
Exactly. R0's solution is, well, it's pretty radical. The core idea is a framework that generates its own training data from scratch.
From scratch. No pre-existing tasks, no human labels, zero.
Zero human data input for the training loop itself. It's designed to be entirely self-contained once you kick it off.
Okay, so how on earth does it do that? This sounds almost like magic.
It does sound a bit like that,
Mhm.
but it's actually a very clever setup. It starts with just one base LLM, think of it as the raw intelligence.
Right, a standard foundation model.
And from that single model, it spins up two independent models, each with a specific job. They call them the challenger and the solver.
Challenger and Solver. Okay, I like those names. What do they do?
They're set up to be optimized separately, but they co-evolve through interaction. That's like a dance.
A co-evolutionary dance. Tell me more.
So the challenger model, its job is to come up with tasks, questions essentially, and it gets rewarded if it proposes tasks that are right near the edge of the solver's capability.
Near the edge. So, not too easy, not impossible.
Exactly. Think of a really good coach or a personal trainer. They don't give you weights you can lift easily, nor ones you can't budge. They find that sweet spot that forces you to struggle a bit and actually get stronger. That's the challenger.
Okay, I get the challenger.
Mhm.
Pushing the limits. What about the solver?
The solver's job is simpler to state. It gets rewarded for solving increasingly challenging tasks posed by the challenger.
Ah, so one makes the hard questions, the other tries to answer them.
Precisely. And because the challenger is always trying to make the questions just hard enough, and the solver is always trying to solve them, you get this targeted, self-improving curriculum.
And this all happens autonomously. No human curator stepping in to say, this is a good question, or this answer is right.
That's the core idea, fully autonomous.
Wow. Okay, let's dig into that challenger mechanism a bit more. How does it know what's near the edge of the solver's ability? That sounds like a tricky judgment call.
It is tricky. It uses what the paper calls a composite reward system.
Yeah.
Several factors go into it, but the really key one is the uncertainty reward.
Uncertainty reward.
Yeah. The challenger is incentivized, like
Yeah.
rewarded, for creating questions where the solver is maximally uncertain.
Maximally uncertain. How do they measure that?
They look at the solver's empirical accuracy. They have the solver try to answer the same question multiple times. If the solver is really confident and gets it right consistently, or if it's completely lost and gets it wrong consistently, the challenger doesn't get much reward for that question. But if the solver's answers are kind of all over the place, maybe getting it right about half the time, let's say its accuracy approaches 50%. That's the sweet spot.
So if the solver answers 10 times and gets it right 5 times and wrong 5 times, the challenger gets a bigger reward.
Basically, yes. That 50% mark theoretically represents the point of maximum information gain for the solver, the point where the task is most efficiently promoting learning.
That is really clever, finding the zone of proximal development automatically.
You could put it that way, yeah.
But wait, what stops the challenger from just asking the same tricky question over and over again?
Good point. They thought of that. There's a repetition penalty.
Ah, okay.
It gets penalized for generating semantically similar questions within the same batch. They use a technique based on BLEU scores to cluster questions that mean roughly the same thing and reduce the reward if the challenger keeps repeating itself.
So it's pushed to create diverse challenges too.
Exactly. Diversity is key for robust learning.
And I saw a mention of a format check penalty. That sounds basic.
It is basic but crucial. If the question it generates isn't structured correctly, like missing the question tags or something, it just gets a reward of 0. Got to ensure the output is actually usable downstream.
Makes sense. Got to follow the rules. Okay, so the challenger is this smart, adaptive question generator. Now, how does the solver actually learn from this?
Right, the solver training phase. So after the challenger generates a batch of these carefully crafted questions, they don't just throw them all at the solver.
No. Wow.
They create a curated data set. There's a filtering step.
Okay, what gets filtered out?
They only keep the questions where the solver's performance falls within what they call an informative band.
Informative band. Is that related to the 50% uncertainty thing?
Sort of. Specifically, they keep questions where the solver, when asked multiple times, gets between 3 and 7 answers correct out of 10.
Ah, so not the ones it aces, 8, 10 correct, and not the ones it completely bombs, 0, 2 correct.
Exactly. It discards tasks that are either too easy or too hard. This focuses the solver's training effort where it's likely to learn the most.
And the paper mentions this also acts as an implicit quality control.
Yeah, that's an interesting side effect. If a question is perhaps badly worded or ambiguous, the solver's answers might be really inconsistent, potentially falling outside that 3 to 7 band. So filtering helps weed out potentially low-quality questions the challenger might have produced.
Okay, so we have this filtered set of challenging but not impossible questions. How does the solver know the right answer to learn from? There are no human labels, remember?
Right. This is another clever part. For those filtered questions, they generate a pseudo-label.
Pseudo-label, meaning a temporary self-generated label.
Exactly. They look at the solver's own multiple answers to that question. The answer that appears most frequently, this majority vote, is designated as the correct answer, the pseudo-label for that training instance.
So the solver is essentially using its own consensus answer as the ground truth to learn from.
Precisely. If it answered A 7 times out of 10, A becomes the target label for that question during fine-tuning.
And then the solver gets updated based on that.
Yep. It's then fine-tuned using a really simple reward signal. It gets a reward of 1 if its subsequent answer matches that pseudo-label and 0 if it doesn't.
Wow. Okay. Challenger makes hard questions, solver tries them, questions get filtered for difficulty, solver uses its own majority vote as the answer, and then learns to be more consistent with that majority vote. It's a completely closed loop.
That's the beauty of it, a self-contained, self-improving cycle.
So does it actually work? I mean, the theory sounds cool, but what about the results?
The results are where it gets really compelling. The headline is that R0 substantially improves reasoning capability across different backbone LLMs.
So it makes existing AI models smarter.
Yes. They tested it on various base models, for example, in mathematical reasoning, which is a tough area.
Uh-huh.
One model, Qwen 3.4b base, got a boost of almost 6.5 points on math benchmarks. That's a significant jump.
6.5 points is huge in these
It
benchmarks.
really is. Another one, Qwen 3.8b base, saw its average math performance go up by 5.51 points over 3 iterations of this R0 process.
And it kept improving, like iteration after iteration.
Yes, the report highlights a progressive improvement, a clear trend of performance gains across iterations. The loop seems to genuinely compound the learning.
Okay, that's impressive for math, but reasoning isn't just math. What about general thinking?
This is arguably the most interesting part, the generalization effect.
Generalization.
Meaning, even though the challenger was prompted mainly to create math problems,
Right, you said it was focused on math.
the reasoning skills the solver learned from those math problems actually transferred and helped it perform better on complex general domain tasks. Tasks it wasn't explicitly trained on by R0.
Whoa, so learning math made it better at other stuff, like general knowledge or logic puzzles.
Exactly. For instance, that same Qwen 3AB model didn't just get better at math. Its average score across a suite of general reasoning benchmarks also improved by 3.81 points. Another model, OctoThinker 3B, saw a 3.65-point gain in general reasoning.
That's really significant. It implies it's not just memorizing math procedures, it's actually improving its underlying thinking ability.
That's the takeaway, yes. The report concludes it enhances the model's underlying capabilities. It's learning how to reason more effectively, generally speaking.
Okay, that's pretty powerful. And what about using it alongside traditional training? Does it help there too?
It does. They found R0 works well as a mid-training method.
Mid-training, like you use R0 first, then do normal fine-tuning.
Sort of, yeah.
Yeah.
They took models, first improved them using the R0 self-evolution loop, and then fine-tuned them on standard human-labeled datasets.
Did it make a difference compared to just using the human data?
It did. Those models achieved higher performance than models fine-tuned only on the human data. The gain was about plus 2.35 points on average.
So R0 acts like a primer. It boosts the model's base reasoning, making subsequent human-led fine-tuning more effective.
That's exactly how they frame it, a powerful performance amplifier. It makes the later expensive human data tuning more impactful.
Okay, the results sound great. But why does it work so well? Did they try to isolate the different components?
They did. They ran an ablation study. That's where you systematically disable parts of the system to see what breaks or how much performance drops.
Right, like taking the engine out of a car to prove it's important. What did they find?
The biggest hit came from disabling the challenger's reinforcement learning, the part where it learns to ask better questions based on the solver's uncertainty.
Ah, the core learning lip for the challenger.
Yep. Turning that off caused the largest drop in performance. For one model, it was negative 3.7 points in math and a whopping 4.1 points in general reasoning.
Wow, okay. So the challenger actively learning how to challenge is critical.
Absolutely crucial. Removing the repetition penalty also hurt performance, showing that asking diverse questions matters.
Makes sense.
And disabling the task, filtering the step where they remove too easy or too hard questions, also caused a notable performance drop, particularly in the general domain tasks, over 6 points lost there.
So that filtering isn't just about difficulty. It really does help with quality control, too, it seems.
It validates that dual purpose, exactly. Difficulty calibration and implicit quality control.
This whole co-evolution thing.
Hey.
Did they actually measure if the challenger gets better at making hard questions over time?
They did. They tested a solver that wasn't improving, a static one, against questions generated by the challenger in different iterations.
Did the questions get harder?
They did. The static solver's accuracy dropped from 59% on iteration 1 questions down to just 47% on iteration 3 questions. So the challenger was definitely learning to generate progressively more difficult problems.
Okay, the system works as intended there. But you mentioned something earlier, a potential issue, a trade-off.
Ah, yes. This is an important nuance. While the questions demonstrably get harder, there's a catch regarding the pseudo-labels the solver generates for itself.
The majority vote answers. What's the catch?
Their analysis showed that the true accuracy of the self-generated pseudo-labels, how often that majority vote actually matches the real ground truth correct answer, unfortunately systematically drops over iterations.
Oh, by how much?
It went from around 79% accurate in the initial phase down to about 63% accurate by the third iteration.
So as the problems get harder, the solver becomes less reliable at figuring out the right answer, even by its own consensus.
That seems to be the case. The paper calls this a critical trade-off and a potential bottleneck. If the AI is learning from increasingly noisy or incorrect self-generated labels, that could eventually limit progress or lead to, well, strange behaviors.
Yeah, that sounds like a potential issue down the line. Training on flawed data, even if it's self-generated.
It's definitely something to watch.
Yeah.
However, despite this drive in the absolute accuracy of the labels, the internal mechanics still work, meaning the solver does consistently hit that target of roughly 50% accuracy on the questions generated by its contemporary challenger. The internal reward mechanism, optimizing for that uncertainty sweet spot, functions precisely as designed. It's always learning from problems right at its perceived limit.
Okay, so the engine is running correctly, even if the fuel quality, the pseudo labels, degrades a bit over time. That's a fascinating dynamic.
It really is. It highlights the complexity of these self-learning systems.
So zooming out a bit, where does R0 fit in the bigger picture of AI research?
No, it's clearly a big step forward in label-free reinforcement learning. Its key differentiator is needing zero pre-existing problems to start with, unlike most prior label-free methods.
Right, the from zero data part is key.
Definitely. It also pushes the boundaries of self-play in large language models. Self-play, like AlphaGo playing itself, was mostly seen in games or verifiable domains like coding before.
Where you have a clear win-loss or a program that can check the output.
Exactly. R0 extends this self-play concept into much fuzzier general reasoning domains by cleverly using internal consistency that majority vote pseudo-label as the success signal instead of needing an external judge.
That's a significant expansion of the self-play idea. But are there limitations, things it can't do yet?
Oh, for sure. The researchers acknowledge the core mechanism of R0 is currently suited for domains where correctness can be objectively determined, like math or logic problems.
Where there's generally a right or wrong answer, even if it's hard to find.
Right. The big hurdle, the next frontier, is figuring out how to apply this self-evolution idea to more open-ended subjective tasks.
Like what?
Things like creative writing or dialogue, the paper suggests.
Well,
How does an AI teach itself to be a better poet or have more engaging conversations when there's no single correct answer and evaluation is so subjective?
yeah, how would a challenger create a poem that's maximally uncertain for a solver poet? That's hard to even define.
Exactly. That's the challenge for future work, extending self-evolution beyond objective correctness.
Okay, so wrapping things up. We started by asking if AI could teach itself without us.
And R0 offers a pretty compelling yes, at least in certain domains. It shows a pathway for AI to create its own curriculum, push its own boundaries.
It's a powerful glimpse into a future where AI might not be so dependent on human guidance for learning complex skills.
Which leads to that final kind of mind-bending thought.
Go on.
If an AI can effectively teach itself to solve increasingly complex problems, maybe even problems we don't know how to solve yet, all without our direct oversight, what does that fundamentally change about how we think about learning itself and what new capabilities might emerge from these self-evolving systems that we can't even really conceive of right now?
That's definitely something to chew on. A future potentially driven by AI learning trajectories we don't fully direct or even understand.
It opens up some incredible possibilities and probably some new challenges too.
Well, that was a fascinating look at R0. We really encourage you, if you're interested, to maybe dig into the source paper itself for more technical details.
Absolutely. It's dense, but rewarding.
Until next time, keep diving deep.